Okay, today we are looking at judging scientific theories. One of the things with scientific theories is that it is sometimes harder to assess for multiple reasons. One, if it has the presence of a legitimate scientist or scientific group, people are less likely to look as deep into whether or not it is not only accurate, but whether it is a correct and valid type of argument or theory. And part of this is just our natural inclination to trust authority figures. They've done multiple studies on this with psychology that when it comes to someone who either is an authority figure or someone who is presenting as an authority figure, they don't actually have to be, they just have to look or act the part. We tend to defer to them. And we do this with doctors, we do this with lawyers, we do this with scientists. The one of the more famous studies was with a shock test where the person in the other room supposedly receiving the shocks was in on the study. And there would be a person in a science like white coat, doctor's white coat, and then the participants would come in and they were told to ask them questions, and if they didn't respond or answered incorrectly, they were supposed to push a button to give them a shock. The shock started off pretty low grade and moved its way up, and of course, as it moved up in intensity, the person supposedly receiving the shocks would get more vocal about not wanting, that it hurts, not wanting to be shocked, they wanted to stop, while the supposed authority figure just repeated, we need to continue with the experiment. And even when the person would question, say, well, this seems to be hurting them, they would just repeat, we need to continue with the experiment. And the question was somewhat, or the theory, or I suppose the hypothesis initially was whether or not, would people defer to authority figures and continue to give shocks, that by the time, if they really were getting these shocks, at the end of this, the last level shocks would have killed them. And a large majority of people, even if they looked on with discomfort and unhappiness, continued to administer the shocks. Only a few did not, but a lot continued to do so because, and then when asked later, why did you keep giving shocks? Well, because the scientist or the doctor said I needed to continue. So if we have that kind of in our mind, that we naturally kind of defer to those in authority, and specifically in like with scientific data, and then especially if it's someone's not as familiar with the science of whatever that data that you're looking at is, or the experiment or hypothesis, we're more likely to then also defer if it's not in our wheelhouse of expertise, if you will. So it is important then to look at how do we take a look at scientific theories, how do we use critical thinking to assess them, and part of it is all the skills we've learned up to this point is a big part of that. But there are some other things to keep in mind too, and we'll talk about the scientific method and all of that. So that's kind of the idea of why judging scientific theories is you can't assume just because it falls under the realm of science that it automatically is a logical and valid argument just because of the topic, if you will, or even scientists, because as we're going to look at with judging weird theories, there are those out there that are on the more unique, unusual spectrum of scientific theories. Some pan out, some very much do not, and so you can't take all of it with just an assumption that it is valid and accurate and has been rigorously tested, because there are people who pretend to be scientists, there are people who are probably not very good scientists, or those that just are going out and not following the best practices for making sure that their process is valid. So the first thing we want to look at here is with science and not science, like what is not science? And some of the ways that this sometimes gets mixed together, if you will. So science is not technology. Sometimes we tend to think of those two as intertwined. Science is a way of searching for the truth, right? A way that uses what often is referred to as a scientific method. Technology is not a search for truth, it's the production of products. a lot of times technology took science and engineering to produce, and so it's made up of excuse me, it's made up of aspects that you could connect to science and engineering, but it's not science itself, right? Technology is not a search for the truth. Technology applies knowledge acquired through science to practical problems, but not something that science generally, that's not the main focus of science, right? Technology seeks facts to use in producing stuff, right? I think that's the key kind of thing with that we could put here. So technology is or the production of stuff. We're using stuff loosely as a term here. But it's, while science is trying to understand how the world works by cataloging scientific facts, identifying general principles that explain and predict phenomena, right? So I think that's sometimes the kind of mix up with that, is that science does sometimes help produce technology, just like math and engineering and other things like that. But technology in itself is not what science is. The other one is that science is not an ideology. Some people say that science is not a way of finding out how the world works, but a worldview affirming how the world is. And they do see it as an ideology. But that's not the case, really, right? At any given time, as it says here, a particular worldview may predominate in the scientific community, but this fact doesn't mean that the worldview is what science is about. I mean, we all are going to be influenced by whatever zeitgeist is around us. We are not divorced from the culture and worldviews and experiences of our current time. No one is. And so, of course, what type of science is focused on, there's often themes you see kind of pop up, which a lot of scientists will be interested in a certain era or time period. And then that changes over time, because we are a product of our environment and the culture and peoples and world around us. So, of course, things that are interesting or that people are looking at often have that, but it shouldn't be conflated with meaning that that's the worldview of people. And that affirms whatever the ideology is, right? Because worldviews of scientists have changed over the decades, and the general nature of science as a way of searching for the truth has not, in that basic level. Of course, there's new scientific discoveries, new scientific structures that are developed, but the purpose of discovering and searching for the truth has remained the same from the beginning. And I think that's important just to know, because sometimes, like I said, you do see this intermixing of science as an ideology rather than it outside of that component. And then lastly, science is not scientism. Scientism is essentially, the definition here is the view that science is the only reliable way to acquire knowledge. It is the idea that science is the only reliable road to the truth. We obviously know many things without the aid of scientific methodology. You constantly are knowing and learning things outside of that realm, and can know for the truth, certain aspects of that. So that's, I think, is the difference, right? Is that science can help provide reliable knowledge and the road to the truth. It is not the only way. And especially when you think about like cultural practices, religious beliefs, understanding like your ancestors or people's practices and cultures, even just like day-to-day stuff that we learn. We obviously aren't learning through scientific methodology. We can know by just interacting with things around us, talking to people, observing what we see and know. But of course, there's also a lot of things that we learn from science as well. It is, the key here with this is it's not the only road to truth, right? It's an extremely reliable way of acquiring knowledge about the empirical world, but it's not the only way. It is often said that science is the most reliable source of knowledge about the world, And I think that works. It's just, again, these are small differences, but it is important to, I think, know and understand them. Is that when you kind of go all or nothing, is where the problem lies, right? Like whether it's an ideology or this idea of scientism, this idea that everything is only through science. That's where it becomes problematic. But science is reliable, and it is one of the better ways of understanding the world around us. So that doesn't negate that at all. It's just saying it's not the only way to do so. And why is science so reliable then? And why does sometimes people then conflate that to mean everything, or the only way to view things is through science? Well, because it embodies to a high degree what is essential to reliable knowing of empirical facts. It is a systematic way of consideration for alternate solutions or theories, and has rigorous testing and careful checking and rechecking of the conclusion, which should sound a little bit like the scientific method in there. If it's being done correctly. I mean, that's one of the things we're going to look at, right? If someone is claiming some type of scientific knowledge or breakthrough, and they're not going through those steps of consideration of alternate solutions and theories, I'm going to put those here, right? So consideration of alternate theories and solutions. Theories, and I believe that's what I said. Solutions. And then rigorous testing. And then careful checking. And rechecking. Right? These things are part of what makes it so reliable, if it's done correctly. So I think that's sometimes where then it gets connected to this other idea that is the only way, because it is reliable, and it is a good way of understanding how the world works, how things function. It's just, again, it's not the only way for us to do that. The next thing is looking at 7 warning signs of bogus science. And this is things to pay attention to. If you see, you should then know that you need to look more closely and analyze what's being presented as science. The first is the discoverer pitches the claim directly to the media. So why would that one be a sign of potential problem? Well, really, it's because it seems like they're trying to bypass peer reviews and evaluation by other scientists by going straight to the media. It doesn't mean that scientists, when they do discover something, won't eventually go to the media. But if they are working by themselves and then present this crazy new idea and they do it directly to the media, that should be a warning sign that potentially they've bypassed those rigorous testing, retesting, checking, and rechecking processes that should have been going on. It essentially, the integrity of science rests on the willingness of scientists to expose new ideas and findings to the scrutiny of other scientists. It's that peer review, right? You need the peer review of, well, I mean, it's in the word peer, but we'll put it here, scientist. This idea that you're making sure that other people in the field are also checking your work, or the other scientists' work, so that they can do their own checks, and also let people know, like, yeah, seems legitimate based on all of this testing, versus someone being like, oh, this doesn't make sense, where'd you get your data, kind of thing, right? It's a good check and balance, that really a process that's expected to happen before someone just jumps straight to the media. Attempts to bypass this suggest that the work is unlikely to stand up to close examination. Essentially, they're trying to avoid other scientists saying that's not correct or accurate at all. They just made that up, right? And they instead are hoping to have the popularity of their idea catch on by people watching the media, so that they can, whatever their end goal is with that. The next is there are claims that a powerful establishment is trying to suppress the person's work. I mean, that should sound somewhat conspiracy theory anyway, But again, this idea is usually that the establishment will somehow stop at nothing to suppress discoveries that might, impact or change the balance of wealth and power in society. I mean, that's usually like mentioned in movies, where some scientist has discovered something, but this cabal organization is trying to prevent them from releasing it because then they'll lose money. But you hear it sometimes too, and the idea that corporations, or like with vaccines and shots, that these corporations are actively preventing some kind of discovery to come through. Another is the claim that oil companies are frustrating the invention of a car that runs on water. Right. That because of course the oil company would lose on money is potentially a sign that the science is not real. Now, again, I think with any of these, you can't immediately dismiss some things. I mean, it might be obvious, and you can immediately dismiss it. But this is where your critical thinking skills should come in if you see any of these warning signs and go, wait a minute. I'm not going to just blindly trust because it has science in the name, or scientist or doctor, right? We actually need to look further into this to see why are they claiming this? Where is the legitimacy behind this, right? That's kind of the idea with any of this, is that what you should do is stop and use the critical thinking skills. And that's going to help way more in making sure you understand when there is an issue. The next one is that the scientific effect involved is always at the very limit of detection. The idea is that, there's you can't, we're just where we can't see clearly something. For example, there aren't clear pictures of UFOs or the Loch Ness Monster. The idea of what telepathy, psychokinesis, precognition. There's lots of papers published in this parapsychology that claims to report verified instances of these things, but it's not clear and direct evidence or proof, right? It's always something small, like, well, we have this, but it can't definitively, it's just always on the outskirts or outside of what would have the direct proof. We just need to find that better picture. While we have this evidence of what would be a good one for that? Telepathy. There was this huge project that was done about telekinesis, telepathy, and several other things, the paranormal science kind of stuff. And there was one of the universities had this whole kind of like think tank thing, and this was like in the 60s, I believe, 60s and 70s. There is a really good podcast on it. The World's Best Con, I believe, is what the podcast is called. And there's different seasons, and one of the seasons was looking at this specific thing. And then where you end up basically two students that were high school students when they started, that conned these scientists into believing that they had these kind of powers through a lot of clever tricks, some knowledge of magic tricks, and some luck. And they had these scientists convinced, but there was always kind of, ways that they worked around this. There was supposed to be this very rigorous testing methods to make sure no one could manipulate it. And it turns out that when you look back on how were they able to accomplish this, if there was all this rigorous data to protect against this ability, as they got to know the boys, they were more lax on some of that, and the boys looked for and exploited any situation they could to circumvent some of those supposed safeguards that were in place. And only when other scientists started looking at it and going, well, you have this data and you supposedly got this, but you can't replicate it. right? Or you don't have any other evidence of this. And also, here's a bunch of different ways the methods that you were using could be exploited. In fact, it was another magician that actually walked them through the different ways that some of these things, the way that they had their methods set up for testing, could be exploited. And so that is that part. I'm actually covered several parts, but again, I think it's the ultimate con, or the world's greatest con. The world's greatest con is, I think, what the podcast. It's the second season. I believe that they did this one. I can't remember now. Second or third season. It's really good. It's really interesting. And the whole season they went through and talked about all that took place with this. And it's, I think, a perfect example of that people so wanted to believe that this was real, along with even the scientists, that many didn't question when they started producing these results that mysteriously wouldn't work on camera or in certain live demonstrations, but only in these certain settings, and people question going, well, if it was true, they should be able to have it take place anywhere, anytime. And now you're saying it's only under, when if they get nervous or how they're feeling impacts that. And that was often an excuse that was used for why it wasn't working at the moment, even though other people verified that they had seen it work in the past. So that critical thinking skills would have come in handy for debunking that a lot sooner than it took it. And actually, they scientists themselves didn't figure it out. The boys end up announcing on TV, live TV, after years of going through all this, that in fact they had conned them and made it all up, because they didn't plan for it to go so long. It was that it was originally just to prove that this was bogus, and then they caught in too deep and they didn't know how to get out without hurting them. And it's, like I said, a crazy story, super interesting, but it fits into that one of that kind of the always on the limit of detection. The next is evidence for a discovery is anecdotal. So this is right. You should distrust anecdotal evidence and for scientific purposes. Anecdotal evidence is perfectly fine in just general conversation, or if you're noticing like, hey, yeah, a lot of people have experienced this and there's a story about this, or this is, I've noticed this to be the case. But the problem is that anecdotes have strong emotional impact, and we're often connected and tied to that. It's also usually very personal. So, right, it's connected to stories and personal experience. And while you can't completely discredit that, if some scientific experience is all, or discovery is all connected on anecdotal evidence, you should be concerned, because that there's no way to, there's potentially no way to replicate or test that, and you can't go just off of this emotional connection alone. The next is the person has worked in isolation. Again, peer groups. Science is rarely is it the lone genius working in their underground lab who comes up with a groundbreaking discovery on their own. Science is usually a collaborative experience that takes lots of people and multiple years to produce, and not done in secret in a basement by one single individual. Not saying it can't ever happen. It's just, again, these are the warning signs. These are things if you see any of these, when someone is promoting some new discovery or solution or answer to something, these were things that when we need to stop and say, let's critically look at what's going on and take a step back and look at the larger picture, because you should be suspicious of it. Again, it's not to say that these can't ever happen. They're just unlikely. And that should be triggering our critical thinking warning bells when we see these. But again, it's these scientific breakthroughs are usually done by multiple scientists working together. It's a collaboration, a collaborative experience. And then new laws of nature must be proposed to explain an observation. Right. I mean, if you have to have a new law of nature to explain some extraordinary result, then it probably isn't, likely. If it's conflicting with the laws of nature that are already known, it should immediately be suspicious of that, right? If we must change existing laws of nature or propose new laws to account for an observation, it probably is wrong. That should just be the warning sign in of itself. All right, so those are the bogus science. Again, bogus science in terms of it is that just these are the ones that I think the only thing I'd say with bogus science, it doesn't mean it always is, but often bogus science has one of these warning signs. So if you go back and look at some hoax or fake scientific discovery, what you should find is there's one of these warning signs is probably going to be present, if not more. And then when we're looking at when things have been proposed that this is some breakthrough, and then it later comes out that that's not true at all, it probably, like I said, they probably at least had one, if not more, of these warning signs in place. So that's the only thing to take away from this is, it's not saying this is like this never could happen, because that's a problem in of itself to be so absolute, but that it's likely you should immediately be stopping and looking more into it. And if you look at bogus science in the past and then these claims, then they fit into these categories. All right, next we're going to look at the scientific method. So the scientific method does involve several specific steps, regardless of the types of procedures or involved or what someone's looking at. And it's obviously meant to evaluate the worth of an hypothesis, which is also kind of the first step from it. And so in sciences such as physics or biology, hypotheses are assessed through controlled experimental tests. In other sciences such as astronomy and geology, this usually must be tested through observation, because obviously there's some that you can actually do physical experiments with, and other types of sciences that you can't. And so, but the idea is that you can apply this to any kind of scientific test you want to do. But sometimes how you do each of the steps can vary slightly. But the idea is, of course, that following these steps helps produce a trusted, valid, ultimately conclusion that you're working to prove your hypothesis. So, of course, the first part is, I can number these and stuff. The first is identify the problem or pose a question. So that you're coming up with, what is it? You have to first decide what you're going to, figure out or test. This should lead you to devising a hypothesis to explain the event or phenomenon. So what do you think that is going to happen, right? So you come up with the problem or the question, then you create a specific hypothesis that says like that, this event creates this thing. Or the one we're going to look at as an example we're going to walk through on is that high doses of vitamin C can increase the survival time of people with terminal cancer. Or the other version of that would be high doses of vitamin C does not increase the time of people who have terminal cancer. So how they got to that was at first noticing that there seemed to be some correlation between people who lived longer with terminal cancer that had higher doses of vitamin C. And so that's how that question became proposed, right? And then once you have your hypothesis, the next is derive a test, implication, or prediction, right? So in this case, it's then figuring out how you're going to test that, which again, with some types of sciences, you can have an actual physical experiment process that you run through and do. Others it might be through observation with data, so that you're evaluating and looking at data. It does vary, right? There's not one set way of coming up with a test or to figure out the prediction. But you do have to figure out this test, and ultimately a test that can be replicated, because that's going to be one of the steps further down. Then, of course, you perform the test. So whatever the test is that you came up with, then you enact the test. And then you would analyze the results. And this, in this part, with analyze the results, this includes retesting. Right, the retestability is an important part of this. Can you replicate it? And if you can't replicate something, it becomes hard to prove scientifically that is a valid, whatever conclusion from it, because you have an inherent problem not being able to retest in any way. Then after you've done several parts of retesting or replicating the test, and ideally, let's say you get the result your hypothesis expected, then you would retest. You would replicate the experiment again. And let's say it also gave you the same results. So then you would replicate it at least one more time. Often the replication process is even much more, multiple times than that. But you have to be able to replicate and get the same result multiple times before you can then accept or reject the hypothesis. If after replicating multiple times you do get the same results, then you should be able to accept your hypothesis as accurate. If you don't, or I guess assess that your hypothesis, accept that your hypothesis is not correct, because that could be the other way. You do the test and it does not prove the hypothesis, so you do it again. Does not prove the hypothesis, so you do it one more time. Well, I now have three or more tests that show that the way that at least the experiment that I chose to do to prove my hypothesis, in fact, did not take place. And if I take into account that my experiment is valid, that the type of experiment I chose to do would, if it was accurate, would produce that result, then I can accurately say that this is not the case, right? Now, obviously, there could be a flaw in the test, the experiment type or test, so that has to be taken into account. But if you're sure that this type of test would produce the results if they were present, then you're at a good point of then saying, yes, my hypothesis is correct, or no, my hypothesis is not. And so that's when you're accepting or rejecting the hypothesis, right? And coming up with a conclusion with that. So if we walk through one so you can see how it would work for this procedure, this 5-6 step, I broke it up into 6, and you see both. Procedure to test the hypothesis, right? So with this, as I mentioned, there was some information that terminal cancer patients lived longer than expected when they have high doses of vitamin C. So the hypothesis became high doses of vitamin C can increase the survival time of people with terminal cancer. As mentioned, the alternate hypothesis that could have been presented was that vitamin C has no effect on the survival of terminal cancer patients. And this is an actual real study that was done. So I'm not just making this up. This is an actual study that was done. So the test becomes, deriving the test, if the hypothesis is true, you would expect terminal cancer patients that are given a higher dose of vitamin C would live longer than the patients that did not get a high dose of vitamin C. Right, that's the expectation of that. So the way to then come up with that test is to say, prescribe high doses of vitamin C to a group of terminal cancer patients as the experimental group. However, you have to have enough data to do this, that you can't just give one group this, right? This is the larger part of the test. You're not going to get the data you need if you only give high doses of vitamin C to a group of terminal cancer patients. You have to have another group that would not receive vitamin C, who would be the control group, right? So you'd have one group that got the vitamin C and one group that's the control group that does not get the vitamin C. This would allow you to compare the survival rates between those two groups. But there's another part to this, because if that group knows that they're part of the group getting the doses of vitamin C, you have, our minds are pretty powerful things, and there's the placebo effect, that if you think something's going to help you, or you think you got medicine for something, sometimes, not always, the placebo effect can take place where we do initially improve or feel less pain or feel better, because our brain has been tricked into thinking that we have something that's going to help. This can also take place with the person giving the medicine, or the vitamin C in this case. So that it's important that you actually do essentially a double blind, is what it's called, so that both groups don't know who they are. No one's going to know. So it goes, the double blind is that no people that are part of the experiment will know whether they're getting the higher dose of vitamin C or the placebo vitamin C, right? You have to give a placebo pill to the other group, so neither one knows if they're getting it or not. And then you with the double blind, it also is that those who are treating them or giving them the vitamin C don't know which group either, because I could accidentally and unconsciously give cues if I knew that like the one group I was giving it to was the vitamin C, and then I knew the next group I was giving it to was the placebo. I could end up giving unconscious, body language clues, or the way I act or things I do that could actually alert the patients to the fact of which group they're in. So a double blind not only has the patients not knowing which group they're in, the experimental group or the control group, it also has the doctors not knowing which group is which either. So they have no idea who they're giving the vitamin C to and who they're giving the placebo effect to. And this then allows for the running of statistical tests to ensure that your results are not a fluke. And their statisticians have a bunch of different methods for determining when experiment results are likely or unlikely to be due to chance. Because of course, you have to also make sure that an outcome doesn't happen just by chance, right? It's just by chance that the group you gave the vitamin C to got better. And so that helps eliminate any of those other possibilities. Then you have to accept or reject the hypothesis. Once you get the results, and if the patients receiving the vitamin C did not live longer, that means the hypothesis is incorrect. But of course, it is important to replicate those. So you can't, even if you get the results and say they did not live longer, okay? So now we have to replicate that a couple more times. And if every time we do, the patients don't live longer, then we know that the hypothesis is in fact not correct. And so that's part of knowing like how to follow, that's how following the scientific method, right? In an actual study, it's all of these steps. It's a long process, but it helps guarantee the that it's correct, that it's gone through all the rigorous process to prove it's true or not, versus again leading into that kind of bogus science where you're like, wait a minute, this doesn't seem right. Another aspect is non-intervention studies, as not all medical hypotheses are tested by treating groups of patients and analyzing the results. This is like looking at like long-term patterns of disease. So if you wanted to track disease or other factors in groups across the United States over the last 100 years, right? You're not looking at individual patients. You're looking at the statistical data. So it's non-intervention. And from that, you can end up learning stuff about like specified population, looking at associations among these that might lead to better understanding of how to control disease in certain populations. Non-intervention studies cannot always establish cause and effect relationships, but they can hit at causal relationships. And they definitely can yield some of the same results that make a strong case for that connection. And so that you see like, oh, look, we've seen patterns in disease patterns or progress through these states or this type of weather or whatever the data shows, which then could lead to individual experiments to look at that. I feel like non-intervention studies tend to be like in the larger picture thing over a longer period of time because they're looking at data points and information rather than doing a specific experiment on a person. But that's how it breaks down in terms of the following the scientific method and stuff like that. So judging scientific theories, right? Theory testing is part of the broader effort to assess the merits of one theory against the field of alternate theories. Because this is important with that, is that alternate theories should always be examined. You don't want to just have, here's the only theory, and then just stop looking at everything else. And the broader effort will involve the application of the criteria of adequacy. Right? We've looked at this. We have looked at the criteria of adequacy before. So you have testability. Testability, again, is whether there's some way to determine if the theory is true. Can you test to see if true? Right? How testable? And obviously, I just mentioned non-intervention hypotheses, but there are ways to test those as well. Obviously, if you know that there's a specific way you can test something, though, to prove it's true or not, is a big important part of it. If you can't prove, if there's no way to test if something's true, like I saw a UFO, and there's no way to test that, well, then that has a problem right there in terms of failing the criteria of adequacy for trusting it, right? And that's where the critical thinking skills come in to say, well, this doesn't prove anything, right? It's a false assumption based on that. The next is fruitfulness. This is the number of predictions, the number of novel predictions made. The next is the amount of diverse phenomena explained, the scope, how much of new ideas or concepts are being covered. Let's put that one there. The amount of diverse. Oops, I'm writing into the other area. So explained. And then simplicity, again, the number of assumptions made. The more simplistic, if you get into, it's not always the case, but it's more likely to be accurate if it doesn't require some complex twist and turns, right? Required to explain an argument or a scientific theory in this case. If you have to twist and turn yourself in knots to make it work, that should immediately have you go, wait a minute, the more simplistic something is, the more likely, or simplistic in answer, right? Or connection, not necessarily whatever the topic is, could be complex, but the process for discovering or the process for having a new theory work. And same thing in terms of just a general argument. If someone is making up some kind of argument and it's so complex, the question is it, is that, making it fit by, going all over the place, rather than it should be more simplistic most of the time. And conservatism, how well a theory fits with existing knowledge. Right, and this one we mentioned, if you have to create new laws of nature, that should already be something that you question. Does it make sense with the existing knowledge that we have, or is it completely something that doesn't fit with what we know? Again, it doesn't always mean that it's not correct. These are just the steps to help you try to determine whether, again, an argument is valid or a scientific theory is valid. You're using the same kind of process. So judging scientific theories with this, we're going to look at how that fits into the example with Ptolemy and Copernicus. And using, again, that method. So before we even get to Ptolemy and Copernicus, right, Aristotle started stuff with putting forth the theory that a spherical Earth was at the center of the spherical universe, consisting of concentric, transparent spheres. And this at the time made sense to people based on the observation that they knew. Well, Ptolemy comes in and found that Aristotle's theory was not conservative fully, that he had kind of taken some new ideas to make that work. And so also it was inconsistent with some of the observations and stuff as well. So it's he immediately goes in and says, wait, this seems off. Let's take a closer look. So he fine-tuned this view with some of the areas that he felt was off, and added the idea that the circular motions called ellipticals were along the planet orbits and many other minor adjustments. He also allowed for an odd asymmetry in which the center of the planet orbits was not exactly the center of the Earth. The result was a system that was far more complex than Aristotle's was. So it was not, the simplicity wasn't there. But the revised theory worked well enough for the time, and it did agree better with than the earlier theory did with observational data. So again, that conservatism, it actually worked better. Even though there was some that worked with Aristotle's, Ptolemy's new theory was even better with conservatism than Aristotle's, right? With the theories that were known, and more specifically with theories that they could observe. The chief value of Ptolemaic system was that conservatism. It fit mostly with what astronomers knew about the celestial structures. The other thing that it did is it was also, so let's put that there. It was also testable. So the testability was there as well. Its biggest failing was as I mentioned, the simplicity. It was not simplistic at all. It worked by being propped up by numerous assumptions for the purpose of making the theory fit. Right? It's that again, that if you have to change the laws of nature kind of thing, if you have to have a whole bunch of other rules and structures to make your theory fit, there's probably some problems with that. Now, Copernicus's theory was simpler than Ptolemy's. So you have simplicity on his side on several areas, but one of the most impressive was the retrograde motion, a phenomenon that had stumped astronomers for centuries. From time to time, certain planets seemed to reverse their customary direction of travel across the skies and move backwards. So Ptolemy explained this retrograde motion by more epicycles, essentially. It just kept adding more into them. And it created a lot of complications. It just created a whole complicated structure, whereas Copernicus's theory could easily explain retrograde motion without all the addition of more and more complex epicycles. So Copernicus' theory was not only superior on the simplicity, but it also tested well with conservatism, because it explained many of the astronomical observations that people had seen but didn't know what to do with them. Ptolemy's theory did as well. Copernicus' theory just also did it not just as well, but slightly. It explained it fit with other observations that Ptolemy's did not. So again, you can have two competing theories, both have the same conservatism. And then you have to then go, well, what about the other theories, criteria of adequacy, and how does that work, right? So that helps. It did conflict with some things they saw, but again, both had some of those issues with it. And so ultimately, people accepted Copernicus's model over Ptolemy's because of its simplicity. And making sense and easier to understand in the process. And so that, I think, is a good historical example of, without even knowing necessarily the scientific method fully at the time, how scientists came to determine and decide what aspect of the planet, theories of planet motion and stuff, was to be taken place. And obviously this keeps getting revised over time. But the way that people then agree or disagree on what model works often, not always, but often fits into following that criteria of adequacy, and also the idea of whether it can follow the scientific method as well. All right, so now we're looking at science and weird theories. So, how is science and inference to the best explanation in the realm that seems to be outside of common sense and scientific inquiry? Well, that can be done from, what can science do with UFOs, ESP, ghosts, psychic predictions, tarot card readings, and such. Essentially, the question is, right, how can you take and apply this to weird theories. That's what we're looking at here. Science and critical reasoning can be useful in assessing these weird claims, just as well as assessing traditional ones, right? So just because, and this is part of critical thinking we've talked about, just because something seems weird or unique, we cannot dismiss it, whether that's an argument or a scientific theory, we cannot just dismiss it because it sounds weird. It might be a warning sign, but you cannot outright dismiss it just for that alone. And so we can follow and use this critical reasoning to look at the kind of weird theories, if you will, to assess the likelihood and accuracy and validity of them. Right? Inference to the best explanation can be successfully applied to these types of theories. And the test formula is really the kind of best way of finding or testing and using against these. It works with the idea of ghosts or monsters as well as just regular everyday issues. So, did I not put the test? Let me go over the test formula again because I thought I put it in there, but I guess I didn't on this one here. All right. Nope. Okay. So we'll go back to this real quick. I thought I made a slide for that, but that's okay. So this idea is, how to use the test method. Oh, I think I put it down further. There we go. I was like, I know I put this one in. So here's the test theory. We'll come back to the other one there. Right, so here's the test theory for it. I don't have to write them all. That's good. So step one is to state the theory and check for consistency. Step two is assess the evidence for the theory. Step three is scrutinize alternate theories. Step four is test the theories with the criteria of adequacy. So, right, we already looked at that. So you do this test first, and then you bring in the test of the criteria of adequacy. And that would then allow you to judge and see, like if someone brings up something with ghosts, or for example, talking with the dead. So, for example, psychics or tarot card reading sometime, but a lot of psychics, claim that they can communicate information and messages from the spirit of people who had died. And I think I'll move those around. I think we'll come back to it because I won't forget the other slide. But let's do this one first since we're talking about the test and theory. So let's look at how we can use the test theory for talking with the dead, right? The psychics that have that aspect of it, right? So the first is state the theory, check for the consistency. Psychics are communicating information or messages to and from spirits of people who have died. Right, that's the theory. So then you test for consistency on that, of how often is this taking place? Is it something that can happen on a regular basis? Right? Is there any time where they can't be doing this? That's just the very first steps. The step two then is the main evidence in support of this theory is the psychic's performance. They typically perform before an audience and talk to audience members who have lost loved ones, and while they can make mistakes, they produce enough correct responses that it seems to be specific enough that it impresses people. It's how they get people to believe it. But the problem is psychics have rarely been tested scientifically. The few experiments that have been conducted, either fails or it's super sloppy methodology, or there's problems with it, and so there isn't. The evidence for the theory is problematic, right? So we could say with talking to the issue with consistency is it's not consistent, right? I'll put them here. Not consistent. It's not consistent from psychic to psychic. It's also not consistent with the psychic themselves. There is a lack of evidence to support. It's anecdotal evidence mostly, right? People who have been to these or have had an experience with the psychic, and the very few actual scientific testing that's been done has either been shoddy or failed, right? Then you have scrutinize alternate theories. The main alternate theory to the psychic's theory is cold readings. And there are some people that are really good at this. Cold readings are when and fortune tellers, tarot card readers, they often do cold readings too. Essentially, you're really good at reading body language and how people respond, the words that they use, potentially also. So you start with something vague, right? And then you watch how people respond to vague. Like I see the color red, or I see a woman, or I see a mother, or I see whatever. And you pay attention to how that person responds, the nonverbal cues that they give. And then you build upon it as you go. And there are some people that are crazy impressive cold readers that can sit there and manipulate. And so they'll still get wrong things. Like I think it starts with the letter, I'm getting the letter M, O, L, and they kind of start going through the alphabet until they notice that a person like perks up or hints at something. And then they go back, oh, yes, it's clear now, an L. And the person like, yes. So it's a name that starts with an L. And sometimes people get so excited, they'll just say the person's name. Yes, it's Lorraine, I don't know, Laura. They're reading that. So a lot of times they aren't guessing the actual name. The person actually ends up giving them information. And this is important. Cold readings work if a person is giving information. If you sit there stoically and don't respond at all to anything, then the person's going to have a lot harder time doing cold reading. But people who are expressive and people who are hoping to talk with some dead relative will often give a lot away. And then there are just people that are really good at cold readings and doing stuff. Sometimes they do stuff before too, but the main theory of how is this possible, alternate theory, is cold reading, right? And this is a known thing that people do. It is done in two ways. Sometimes it's done straight up to con people. The person knows they're doing this, and they know they're not psychic, and it's strictly a con or for entertainment purposes. Other times, there are people that are probably just naturally good at cold reading, and instead of understanding that's what they're doing, they do believe that they actually have psychic powers. And then step 4, test the theories with a criteria of adequacy. So now applying this to the two competing explanations. One, that the person actually has psychic abilities, or they're just doing cold readings, right? So first we must judge the theories in terms of scope, simplicity, and conservatism. So, right, in each of these criteria, the idea of cold readings is superior. It is more simplistic than trying to explain a psychic and how that works. Its scope it covers all kind of possible methods for that, and its conservatism is something that we already understand and know how it works, right? Again, it doesn't discount it completely just from that, but that's right there. You can say, okay, theory 2, cold readings make sense. Then theory 1 explains only that psychic's performance, but the theory 2 of cold readings explains the performances plus other kinds of seemingly psychic readings, such as tarot card readings, fortune telling, mentalist, and spiritualist. So again, that scope, cold readings account for all of those, right? Whereas the first one, that psychics are actually just psychic, only covers for psychics. It doesn't count for how tarot readings work or mentalist and other things like that. So the idea of cold readings has a much broader scope. Then the other issue is the theory 1 of just being psychic fails the criterion on simplicity because it assumes unknown entities such as spirits or unknown processes, right? It can be super complex, where, of course, the cold reading doesn't make any such assumption. And then finally, with, again, the psychics, it conflicts with everything we know about death, the mind, and communication, where cold readings fits with existing knowledge. And therefore, as you're assessing this, right, by going through the test formula and then the criteria of adequacy, we can have a pretty good understanding of whether psychics are real, or at least an individual psychic that is suggesting. It gives you both, I think, psychics overall, and then you could use this for an individual psychic if they were claiming that as well. So that's how you'd use it to test. So you could do this for ghosts, you could do this for UFOs, right? It does work. You don't just automatically dismiss weird science theories and stuff offhand. There are some types of mistakes. This is the one again, sorry, out of order in there. There are types of mistakes that I think you want to pay attention to that again are connected to often this kind of weird science. One is leaping to the weirdest theory, believing that just because you can't think of a natural explanation or a phenomenon must be paranormal. So this is common sometimes that you see the lights in the sky. I remember there was one with, I forgot what the satellites were called, something Link, the Elon Musk's satellites for their internet. And what they, in certain areas, you can see them across the sky, and it's a dot of lights in a row, and you can actually see them moving. And people saw this, and immediately, instead of thinking satellites, thought UFO, alien, something like that. That's jumping to the weirdest potential theory, rather than saying, okay, well, what else could the lights or things be? Which is, well, satellites makes the most sense. Mixing what seems with what it is. So mixing what seems with what is the idea that thinking just because something seems real, it is real. A better principle is it's reasonable to accept the evidence provided by a personal experience only if there's no good reason to doubt it, right? You can't, thinking that just because something seems real, it is real, is a big, huge problem. It appears to be, so that's the mixing what seems with what is, right? Seems to be versus what is, right? Just because something seems to be doesn't mean it is actually that. We should always be looking at something, if something seems real and appears, like, again, magicians are a really good example of that. Magicians are really good at making something seem a certain way and appear real. When once you learn how they do the trick, you realize that's not the case, right? Magic being real versus the magicians having certain types of props that allow them to create the illusion that magic is real. Misunderstanding the possibilities. Misunderstanding the logical possibility and physical possibility, and also believing that if something is logically possible, it must be actual. So the idea of just because something is logically possible doesn't mean it actually in actual space or physically can be. And so understanding the difference between logical possibility and physical possibility. They are different and they don't always overlap. But just because something logically makes sense doesn't mean physically it does or that it works. So that, and these are easy to fall into. That's why I would put these on here, because these are super easy to kind of just slide into and not think about, because we do often want to believe in this kind of weird theories. And if something tricks our mind and what we see with our eyes, we want to kind of bypass critical thinking and just go to what it seems to be, rather than stopping and critically think. So this is, again, another way of avoiding mistakes in critical thinking in with these type of events. And it's more common, again, why it was put under the weird science is because we often do this way more with the kind of paranormal magicians, mentalists. People want to believe, and we're more easily swayed when we seem to see that taking place. And then we kind of forget the critical thinking components in the process. All right, so that's looking at, again, the importance of critical thinking in science, both in kind of the weird, more outlandish, paranormal types of theories, and also just regular stuff as well. That it's easy when it comes to science and scientific writings and proposals and data to forget that we still have to look at it with a critical eye, because you really do need to not just assume that all of the scientific methods and processes that are important have taken place. And so hopefully that helps you show some of the ways that are either warning signs that you should look at it more closely, or be aware of how we kind of can trick ourselves with these simple mistakes, and then the proper way of going through and assessing whether some scientific theory fits and is a valid logical theory, and usually either then a logical conclusion or point argument that they're making, or whether it has some holes, some problems in it, and that we don't just trust that it is accurate and correct because of the authority component that scientists and scientific data can often play in our minds with. All right.